Brandon Hilliard from JPL talking about unveiling the origins of dust gap and ring structures observed in protoplanetary disks.
Hi, I'm Brandon, and I am a recent Master's of Physics graduate from Cal State LA. I'm also a PhD prospective student, so please look out for my name in the future. So today we're going to be talking about dust gaps and ring structures in protoplanetary disks. As Juliet just described in great detail of multi-planet systems. In our systems, the ones that we're observing, we are going to situate planets inside of our protoplanetary disks, but not multi-planets. So it's only going to be a single planet interacting with the disk for our study. So let's get moving. So we know protoplanetary disks are full of gas and dust, and we can see this in our artistic rendition of planets. These two tiny little dots located in here, they cause drops in brightness in the overall intensity profile from the young protostar. So this drop in brightness causes a measurable gap that we can detect with interferometers such as ALMA and SMA, which we'll be talking about and more right now. So this study was motivated by the D-Sharp study. We know that the D-Sharp study was huge and provided lots and lots of information about 24 disks, and we got to see many different morphologies, which was groundbreaking for protoplanetary disk evolution. So how is it that protoplanetary disks are related to our protoplanets? Well, of course, they are the birthplace for our planets. And by visualizing these detailed substructures, we can determine the gap properties and relate them to how planets can open up such a gap. So like I said, we're going to be situating a planet inside of our protoplanetary disk. And by planet-disk interaction, the two main physical concepts that allow for the gap to open are gravity, where the planet interacts with this gaseous protoplanetary disk, and the exchange of angular momentum. So there are two types of resonances to consider inside of our disks. They are the Lindblad torques located with the spiral density arms that are connected to the outer and inner portions of the disk, with the planet located in the middle. And then we have the co-rotational resonance that also acts as a way to provide a resonance to the disk. So basically, in a planet-disk interaction, the main, for opening up a gap in particular, we have to have a large torque in order for this to happen. So there are three types of ways that the planets can interact or migrate, so inward, outward, but also based on the size of the said planet and what actually happens to the disk. But for the purposes of our time constraints, we're only going to be talking about the gap opening in type 2, where we have a massive planet, Jupiter, proto-Jovian sized planet. And because it's over 25 to 30 Earth masses, it's on a magnitude that's large enough to overcome the viscosity and gas pressures within the disk. So let's see what that looks like. So we have a star located in the center. This is a surface density hydrodynamical numerical simulation where the planet is located on the right, and we can clearly see a gap being formed. It's stationary, which is a little confusing, but the main point here is that for a large enough planet, we're able to open up a gap by these Lindblad torques dominating the structure. So now in my project for my thesis, I conducted a study on 3 disks in particular, but this was also extended to a few more disks afterwards. AA Tau, AS209, and Elias 2-24 are all transition disks, and they're all less than 10 million years old. So they are very young disks in the class 2 YSO stage, and they are great targets to look at because, one, we have ALMA data and we have SMA data, so we can compare both of those structures to see how they compare and find necessary constraints on these parameters. So we took a very systematic approach to our disks. We did not want to study each gap in super detail. We only wanted to know the gap position, the gap depth, and the gap width. And from that, we were able to plot them and then see how their intensity profiles varied with respect to the radial distribution. From there, we also applied this planet-disk interaction theory and situated one planet inside of our disks, and then applied a dust growth model, one being the radial drift and the fragmentation limits. So that would allow us to come up with estimates for the size of the dust, which was not taken into account in other previous studies like our work. And then finally, using the constraints from the SMA and ALMA interferometric data, we're able to come up with a reasonable planet mass for some of the targets, but not all. So let's get going. We also have our continuum emission images to compare how the intensity profiles are related to the actual plotting. And we can see that the rectangular wells represented the drops in brightness from the star. So like so, you can see a very wide gap located here at AA tau, and it corresponds to a very dark drop in brightness located there, and so on. You can see how all these disks vary, and there is no real reason or real property that is known about why these gaps are opening in such a place. So again, the theory that we use is planet-disk interaction to determine how these gaps can open. So we take the SMA data, which has been constrained, and we've been able to fit power law profiles in order to find the global structure for the disks. So that's what represented by the green, red, and yellow lines. You can see that the overall distribution follows very similarly to the ALMA data, which is the blue, purple, and orange lines. And then you can also see how, if the gaps were removed, how these plots, how these structures are similar if you ignore that there are gaps there. So this allows us to make determinations for how the temperature and surface densities are behaving in those locations. So that provides us with more ways to calculate the unknown variables from our disks. So going back to the fragmentation and radial drift limits, we know that fragmentation occurs when we have large particles crashing into each other like big mud clumps fighting in the playground or something. And you also see the radial drift limit here, where large particles also drift towards the central star or become trapped in the ring. So depending on what part of the disk we're talking about, we can see how these particles are being trapped. So that's a huge part of what goes into determining how the dust and gas gaps are related. So one thing I should mention again is that the dust gaps and gas gaps are not exactly the same thing. The dust gaps is what ALMA is reading because, of course, it's reading the dust continuum emission, whereas gas gaps are what is coming from the simulation or the theory. So we need a way to correlate the dust gaps from our interferometric data to the actual theory of the gas gap structures. So from the Zhang et al. 2018 paper, we found an equation that correlates all these parameters that we found out from step 2, and we were able to come up with a reasonable approach to finding out a planet mass. So the H represents the disk aspect ratio or disk thickness, and it's related to the square root of the temperature. Alpha is the viscosity, so how well angular momentum is being transferred is inversely proportional to the surface density. And K prime is the actual most important part of the project. Is constraining that is the biggest challenge, because it varies by 6 to 5 orders of magnitude. So it turns out if we're not within about 3 orders of magnitude, then there's a huge variability in the planet mass, as noted by this equation. So you see that the stellar mass and K prime are the most valuable parts of the planet mass calculations, but of course the disk aspect ratio and alpha also play a role in that calculation. So really quickly, we can see how the disk aspect ratio changes with increasing how it affects the gap opening. So the Lindblad torque's located with the white. You can see it dimming as it increases. And then also, you can see how the planet mass interacts with the disk and opens up a gap really quickly once it gets to about 100 Earth masses. So that makes sense, right? So based on this information from planet disk interaction theory, we came up with estimates, and if the planet masses were not over 25 to 30 Earth masses, then we were not able to find a reliable calculation just based on that alone. So it turns out we have two reliable estimates for AA tau. We have Jupiter mass calculations between 3 to 5 Jupiters. And then for Elias 2-24, we have about 1 Jupiter mass. AS209 got a very, very low calculation because K prime was also too low. And this has to do with the relationship between the dust gap width being too narrow and also being too far away. So this is located at 60 AU versus 20 AU. So planets that are located closer to the star resulted in higher planet mass calculations. And if they were also too narrow, that also resulted in a very low planet mass calculation. So that's about that. We could also estimate the planet masses at other locations, which we were able to find out, and we saw a lot of variability in that. And again, we see that those planet masses are very low when we continuously move them farther out. And also, here are the other 5 targets that we looked at in our study. Turns out that this one was not so great because the dust gap width is too narrow. This target also got a good result, and the others also had pretty low values as well. So that's about it. Thank you, guys.
Great. Thank you very much. Okay, let me go back and check if there's any questions already in there. I'm not sure. Oh, Patrick, I think was asking a question about the last one, it looks like. So I have a very naive question, I think, because I don't work on this sort of thing at all. What sort of like false positives and sources of noise and things like that do you have for these gaps? Like what are the physical sources of your uncertainty in estimating the planet masses, I guess?
Right.
Does that make sense?
Right. So the main variability comes from ALMA. When I'll go back to that's the original plotting. So here, these plots are based on derived data from the MCMC fitting profile that was not done by me, but instead was just data collected. So we do have fairly low chi-squared values. So statistically, we were able to come up with reasonable values from that fitting. So the fitting profile was done before I got to this work, and it was hugely valuable. But there really isn't a whole lot of variability. There, of course, are error bars within all of these results, but yeah, I hope that answers your question.
Yeah, it does a little bit. Thank you. And it looks like we have a question, or sorry, how much time is left? Is it 2 minutes, Colby, or 5? There's 1 minute left. Okay. So your question from Swastik C is, can there be outward migration, condition for outward migration? What are the conditions for outward migration? Typo, I guess. Will it affect the final planet mass?
Right, so outward migration can definitely happen. It's less likely to happen, but it usually occurs for positive surface density profiles, steep positive density surface profiles. So that means that it does not follow the typical minimum mass solar nebula modeling, which is very similar to our work. Basically, most of what we know about these structures is that they behave like this minimum mass limit. That's just based on what we've been doing. But are certainly disks that do allow for outward migration. It's just that that was not something that we considered in general for our work.
Great. All right. Well, thank you again, Brandon. That was a fantastic talk.